Kayla Leonard, and I'm an undergraduate student at UW.
I'm Brandon Safan. I'm also a first year student here at UW.
I'm Adam.
I'm undergrad at UW Madison.
I'm Pine. I'm a student from University of Minnesota, Twin City, and I'm working with Better Sewers.
I am Julio Estrada. I'm currently with Surge as well. I'm from Beyond the Community College.
Hello, I'm Chris Fellas. I'm a postdoc at the IceCube in Korea.
Hi, I'm Mason Austin. I'm an undergraduate at Marquette U.
I'm Ian Artsinger, undergrad at Marquette with Dr. Andy.
I'm Dominic Battaglia. I'm an undergrad at Marquette University.
I'm Dawn Williams. I'm a professor at the University of Alabama. I'm the analysis coordinator at IceCube, and I also help coordinate flasher data analysis for those of you who are working on that with Surge this summer.
Surge Sinoy, professor at UW River Falls.
I'm Francis Halton. I'm the principal investigator of IceCube.
All right, well, again, welcome everyone. So, get in the discussion. So one of the things that I think I often get asked, or maybe is a sort of a hard thing to get your mind around, is what is the relationship between this institute, which is the WIPAC, which is the Wisconsin IceCube Particle Astrophysics Center, and IceCube. So, WIPAC is the so IceCube is a large-scale facility that's been constructed by the National Science Foundation in concert with other significant funding from foreign institutions, in particular Germany, Sweden, and Belgium, and Europe. But also the entire collaboration now, we're in what's called maintenance mode, or operation maintenance and management called maintenance and operations mode. And the maintenance and operations is actually jointly funded, again by the National Science Foundation, but also with contributions, real contributions in cash and labor from the extended collaboration, which is, I should have put up the collaboration slide here, but the extended collaboration is something like, I've lost track now, but it's something like 48 institutions in, I guess, a dozen countries, and it comprises probably 350 researchers, just researchers alone. That's not to include other people like technical staff and technical and administrative staff. So WIPAC is sort of it's the host institution. It's kind of the laboratory. We sort of model it on the CERN. Of course, we're not anywhere as big as CERN, but we model it on the CERN model, where CERN is a laboratory that hosts experiments such as ATLAS and CMS. WIPAC is a laboratory or a host institution which principally hosts IceCube, but as I'll get into later, we also we are expanding and looking to keep expanding on other particle astrophysics experiments. So we're about 104 people here at the university, at UW. Well, actually, inside this research center. 5 of us are faculty, and we've got on the order of 24 grad students, about 10, a dozen postdocs, and about 24 undergrads as well. So this is our mission. I mean, our mission is actually, first and foremost, again, this is why we're here, to educate and train new researchers and leaders in the field. So that's our principal thing. We get most of our money, or I guess our operating budget, comes from the cooperative agreement that we have between the National Science Foundation and the University of Wisconsin. And that allows us to do all these wonderful things. And again, like I said, this is also supported by this international collaboration. But we also, one of the things that we do here is we do have technical staff. We have engineers, probably 3 or 4 engineers here within WIPAC. But we also have a close working relationship with a laboratory, another research center at UW called Physical Sciences Laboratory. That's out in Stoughton. And that's actually it's a huge machine shop. It's if any of you get a chance to go visit PSL, there's a lot of very interesting stuff out there. There's a machine shop, production facilities. They do all sorts of things, not only for us and for the university, but they also even do some private industry work. We actually built 60% of the visual optical modules were built at PSL, and the drill, it was the hot water drill that was actually that drilled all the holes, was completely supported by the technical and administrative staff at PSL. So that's again, it's not exactly us, but we have a close working relationship with them. And so as a byproduct, not only here but with our relationship with PSL, we can actually support rather complicated engineering designs. In and support complex project structures. Not only for IceCube, but for other experiments as well. So this, leads over into developing innovative instrumentation. So this is I'm sure all of you have probably seen a picture, one picture or another of a digital optical module. This is, I can't remember, it may have been the last one going down, I forget now. This was actually principally designed at LBNL, but what we're doing is we've actually completed an upgrade of this. This board was actually designed probably, last revision was 2005, but the real design probably stems from something like 2002. We've updated this thing with modern circuit boards as a springboard for new deployments of new optical modules and a new upgraded detector for IceCube. And then, of course, we support a lot of outreach and communication. So we have a communication staff which does coordinates press releases. We have quite a bit of outreach activity. So we go out to high schools, museums, science fairs all around the United States, and even support some activity around the world, distributing movies, film clips, whatnot, and even doing some mass media blitzes. We have a couple of interesting, I don't know if you've seen them, but if you Google IceCube on YouTube, there are a couple of nice short 3 to 5 minute clips that are kind of interesting that shows you what they're doing. And we continue to do that. So, so within the organization here, we have an IT staff as well. We actually support a number of computing clusters. We have about 2,000 CPU cores, although I think that probably, we always normalize these things. We always see something like 4,000 cores. We have now well over 250 GPU cores. One of the big computing resource needs in IceCube is actually simulating the data. We've got data, the detector is running 24/7 and 365 days a year. And what we have to do is we basically have to simulate all of the cosmic ray activity. We've got 3,000 hertz, 3,000 cosmic ray events per second strike the IceCube detector and trigger it. And in order to understand how the IceCube detector reacts to that background, ideally we should be simulating, what is that, 3,000 events per second. It's like 50 billion events per year. And because you have to track a lot of photons in the ice has some really complicated optical properties. This actually turns out to E-flow. We don't even quite keep up. So we can maybe simulate 25 or 30% of the lifetime of IceCube. So we're trying to keep on expanding these clusters. And we store the data here. So the IceCube generates, it's the data rate actually coming out of the data acquisition system is about 10 megabytes per second. If you add that all up, it's about 900 gigabytes per day. And what is that? It's about 350 terabytes per year. That's just the real data. Then of course we got at least that much for the simulated data as well. So we generate about a petabyte of simulated and experimental data per year. That's got to get stored somewhere. So we've got 5 petabytes of online storage here, and we've got some data curation archives that are supported at LBNL and in Europe at Daisy Gooden. The detector is rather complicated. I mean, I'm sure that's kind of an understatement, right? It's a rather complicated beast, and it requires doesn't require constant babysitting. It actually is a fairly stable detector. That's one of the nice things about going in the ice. Is the ice is cold and nothing moves. But still, we have 2 people down there right now, the so-called lunar rover experiment operators, and there's an entire staff of about a half a dozen people up here, which make sure that basically the lights are on and the detector is actually taking data in the way it should be, orchestrating monitoring of the data, overseeing that the data is transferred properly from the South Pole. And that's just what I call the daily operations of IceCube. So this is really our principal activity here. So that we provide services for the collaboration. So this is a relationship with a collaboration. The collaboration is this worldwide collaboration of, as I said, 358 researchers. Some of us, which are here. So we kind of play a dual role. I mean, I'm not only a member of the management and operations team, but I'm also one of the IceCube researchers. So I do research on IceCube data as well. But since it's there's so much data coming through, and there's a lot of sort of common activities that need to be that the entire collaboration benefits from, we sort of do mass data filtering. So we filter the data from raw and process it up to a certain level, which is of interest pretty much to everyone. And then the collaboration then can take that the so-called level 2 data and derive various scientific data products from that. And we also oversee the simulation, manage the simulation production. We're the principal conduit between the National Science Foundation and administer the SummerWorks and basically all the resources within IceCube. And as I said, we PR and press stuff. There's some ongoing, I would say, technical activities such as DOM calibration. If you get a chance to speak with Chris Wendt, he's probably got the most knowledge of anyone in the entire collaboration about how DOMs are kind of the low-level details of DOM calibration. And then we pursue new initiatives here. So one of the things that we've been working on and in the last couple of years is deploying an array of simulator, not tanks, but simulator sheets or simulator planes, panels at South Pole we say for snow mitigation. It's actually what happens is that ice top tanks are being covered by drifting snow, and in order to understand the response of those tanks under the constantly accumulating snow, some of them have well over a meter of snow on them now after several years. We're trying to deploy this simulator panel array over basically over the footprint of ice top, and that'll basically give us another ice top that gives us some additional surface shower physics as well. So that's kind of one of the big new initiatives that we got here, in addition to pursuing new projects, which I'll get out to later. We support not only IceCube, but ARA or RF, which is a radio experiment, kind of still in prototype phase, in the field off the side of IceCube. Hawk, which is the high altitude water terrain tug experiment in Mexico, on a mountain in Mexico. You can see some of the tanks right here. CTA, which is an array still to be built, a future array of terrain tug imaging atmospheric terrain tug telescopes. That's, you can actually see it. It's artist rendition right here. This is gamma ray. These are both gamma ray, principally targeted to gamma ray physics, not neutrino astrophysics, dark matter, and then future IceCube, as well as even some accelerator studies of neutrinos. So CHIPS is a potential detector to be deployed in some mine pits up in northern Minnesota, receiving a beam from, kind of parasitically receiving a beam from Fermilab to home state. And then, yeah, this one. Move on. All right, so again, why do we run these boot camps? Because we want you guys to learn how to use IceCube software and tools. And it's, as you'll see, there's kind of a steep learning curve, and the documentation, this is actually one of the principal conduits of documentation. Soak it all in, because we need you to actually understand how to use the IceCube software, make it better, and we rely on the collaboration to actually provide software services. So if any of you are in particular really just love programming, you may actually find that you can help out and serve on one of these, for example, strike teams. These kind of dedicated software teams, which really get into the murky details of software development. It's a good, it's just a really fantastic sort of system that you can that you can get into if you really like writing software. It gives you a good introduction to kind of distributed software collaboration on large projects, large complicated projects. And of course, you can understand the detector better and even think of new ideas for making IceCube better, maybe making new reconstructions or even new analyses. And then of course, pass it on, mentor the students that are coming in behind you as you progress in your academic careers. And then of course, finally, I'll put a pitch out here. So every year in roughly, I guess, December or January timeframe, we have to solicit new winter rover operators. There are basically 2 new people that come in every year and serve. Some of them are repeat, but most of them are actually new. And if you have the chops for spending an entire year at South Pole, I personally don't, but it's each his own. Pay attention to these South Pole posts. They're posted on our website. You can also find them at just the UW job posting. And there's usually a mail that goes from Ralph Howard to IceCube C every year. Consider doing it. I'm sure it's a fantastic experience. I just wouldn't want to be there trapped there for a year. All right, so I'm going to quickly go through some Amanda history, and then I'll turn it over to the technical people. So it all started out in the 90s, and I started. I've been with the project since 2000. So I was actually I kind of even post-date. The last deployment of Amanda strings was in 2000. Wait, was it? Yeah, 2000. That's right. I joined actually right after January 2000 was the last deployment, and I joined in April of 2000. This is what Amanda looked like. I mean, just to give you, I don't know, you'll probably see scale representations of what the IceCube detector was. And IceCube would kind of expand, something, fill the entire screen here. But Amanda was a relatively shallow detector to start out with. That actually was in the early 90s, 1994, so-called Amanda A, where they deployed this little green cylinder up here, just I think it was 80 modules if I remember correctly. There was a lot of bubbles in the ice, in the shallow ice, and so I don't know. Somebody had the foresight to keep on going deeper to get rid of the bubbles. The bubbles obviously they cause scattering, and you couldn't reconstruct anything up at the shallow depths. But they persevered and went deeper, and finally the last sort of deployments of Amanda were Amanda B, which you see here, and Amanda. Wait, is this B10 or this is Amanda? Should be Amanda 2. No, I guess this is just B10. I actually don't have a picture of Amanda 2. Well, this is B10, which had. Oh no, that's right. This is yeah. So B10 is actually the red cylinder right here, and that's it was 10 strings that were deployed between 1,500 meters and 2,000 meters. For reference, IceCube is between 1450, and even goes a little bit deeper here. It goes down to 2450. And then finally, there were these 19 strings were finally deployed by 2000, and Amanda actually continued to run until about 2000. I think it was 2008 or 2009. I think it was 2008. So this is all pretty much all analog readouts. So the pulses were actually they came up over either coaxial cables for Amanda for some of the core of Amanda, or twisted pair cables, but they were ultimately analog signals. And as those signals, as the 10 nanosecond-ish PMT signals propagated up those, what was that, at least 1,500 meters of twisted pair cable, the 10 nanosecond analog signals from the phototube got expanded into about 300 nanosecond pulses. So things are pretty slow, and we use kind of conventional surface electronics, pretty much based on KMAC instrumentation, to digitize the waveform. To actually, all we did was basically look at the peak height of the waveform and recorded the time of arrival, basically the threshold crossing times. And it was a real chore to kind of analyze data, and of course there's all kinds of crosstalk. In the later strings, so the outer strings here outside of this red module, and so all the things outside of the inner circle here, actually had optical fibers, but those actually were pretty dainty and a lot of them didn't, like 20% of them didn't survive the refreeze. And although the optical fibers had the advantage that you could preserve that fast pulse timing. And then of course there was string 18, which was the first digital string. It was actually, the digital side didn't really work that well, so we fortunately had an analog readout as well, but this was kind of, string 18 was kind of the prototype of IceCube. And then finally, you may notice that there's a string, let's see, I guess it's right here. This is the famous string 17, which actually got stuck shallow in the ice, and it wasn't really used for much. I remember one time as a grad postdoc, I actually constructed a mule that went all the way from the top of string 17 all the way down to the bottom of string 13, but that was kind of a novelty event. And yeah, anyway, that was a very good learning experience. We learned how to basically make digital or optical modules, but in scaling, trying to think about scaling those in the end there were 677 optical modules in Amanda 2, and thinking about all the labor that was required to calibrate them, scaling to 5,000 modules just wouldn't work. So we ended up going digital, and that was the optimized version, which is called IceCube. So IceCube cost about $300 million. It was actually, I guess, $280 million to construct. That was not just equipment, but that was the entire project cost. It's a little bit of trivia. They were actually very early. A lot of people think that the first DOMs that were actually deployed in 2004, actually January 2005. That's not exactly true. There were a couple of early DOMs that were called, there were two DOMs called Franken DOM and Scarface that we sent down, and they're still there actually. They're deployed on the surface and actually formed the kind of first prototype ice top station. They looked a little different than the DOMs that we finally decided we put down, kind of the production DOMs, but they operated pretty much the same. And they probably actually still would work, I would guess, but obviously they've been turned off. They're not interesting to anybody. So we ramped up pretty quickly in IceCube. I remember I came to Wisconsin in 2002. The project had really just sort of kicked off and was starting to get funding. And 2 years later, we had to start putting DOMs in the ice, and those were 2 pretty hectic years. And over the next 6, by fall 2004, we built 400 DOMs, actually all in the scale of about 6 months. That was, we actually ramped up our production facilities pretty quickly, and we tested them all and shipped them all to South Pole. And then over the next 6 years, there were 3 production sites, one here, one in Germany, and one in Sweden. And I think we made finally about maybe 6,200 modules. We still have, actually it's funny, we still have about 100 or 120 modules sitting on a rack out at PSL that would, some of them actually went to poll and came back. They just, they weren't used. There were no holes for them. If we drill again, you can bet that I'm going to lobby to get those DOMs on the ice because they And I don't mention here at all the, the drill. I mean, obviously there was a lot of drill effort. That was, this is a 4.5 megawatt power plant that drilled all these holes. That was a big, actually, that was a huge aspect, huge portion of the of IceCube. All right, just two quick slides on the future. So eventually, what we want to do, IceCube is, as you'll probably hear, IceCube is, it's been great for detecting the flux of cosmic neutrinos, but the event rates are just too small. It's hard for us to really accumulate sufficient statistics in order to really understand what's going on. We still haven't detected any point sources of neutrinos, and that's what we ultimately hope to do. So the plans are to build, go bigger, go bigger and better. So here's IceCube right here. The plan is to actually deploy what's called IceCube Gen 2, which is this kind of D-shaped thing right here, object. It's about 10 times the size, the aerial size and volume of the IceCube detector. In addition, we would actually propose to potentially outfit the surface with an even larger array of, let's say, simulator tanks, so that you can do air shower physics and deep towing on a large scale. And then finally, there's this outer ring of potential array of radio detectors. Now, radio is actually at very, very high energies. Radio starts taking over from the optical as being the more efficient way of detecting ultra high energy neutrinos. At this point, the crossover point is around 100 PeV, which is, that's well above the, our highest energy event is something like 10 PeV. So another order of magnitude. But if you want to go hunt cosmic neutrinos or even explore the scale of the existing astrophysical neutrino flux, you would probably want to build a larger detector like that. So this would be really a fantastic facility, broadband going potentially all the way from extremely low energies. If we have infill arrays all the way up to the highest energy cosmic rays. In order to get there, it's a challenge. Got to find money. What we proposed is to build a very, very first effort to just kind of get the drill going and to kind of get our experience back with deploying things at South Pole, and then of course also doing some interesting physics at the South Pole. So we hope that on the short time scale, let's say the next 5 years, we will get some money to deploy an infill array, which you can see is going to, here's the IceCube in the blue, E-core, which is our current infill array, and even denser instrumentation, on the order of 20 meters DOM spacing between strings, and on the order of 2 meters between DOMs themselves. You can kind of get an idea of the different scales of the instrumentation density here. This thing would be a very powerful detector for probing atmospheric neutrino basically sound neutrino properties from atmospheric neutrino beams, potentially putting more constraints on the unitarity of the neutrino mixing matrix. We can do much better neutrino oscillation physics, but also can do ultra high energy. We can actually, even this small detector can improve ultra high energy astrophysics by characterizing the ice better. One of the biggest systematics that we have in IceCube right now is we just don't really know all the ice properties. It's a very complicated system. It's nice because it's free, but you have to deal with what nature gave you, and we don't really still know everything about the ice. So we would be able to use this system to improve our knowledge of the ice, reduce systematics, and then we could actually apply this to all the data from IceCube, even going back 10 plus years, to get better reconstructions and better sensitivity to point sources and flavor physics too. Okay, so that's already way over time. I'm just not going to even go over this. I'm just going to say, enjoy your week. Get out and view the social scene too. Madison is an extremely nice place to be in summer, and make friends, yada yada yada, right? And I hope you not only have a enriching intellectual experience, but an enriching social experience during this week. Thank you. Now I believe Francis. I can tell you what makes these signs.
Are there any questions?
No, it was perfectly clear, of course.
Okay. So I am obviously, IceCube has been pretty much described by this time. And beyond IceCube, what we are going to do next, Gail just discussed. So I'm going to concentrate on the discovery of cosmic neutrinos and what their sources are. In fact, I'm pretty much going to cover this, and Alike Randish, who's talking after me, will discuss the question where cosmic neutrinos come from. So let me try to remind you why, what neutrino astronomy is. The idea of neutrino astronomy came up immediately after the neutrino was discovered, because you didn't have to have a physics degree to realize that the neutrino was like a photon. And so since 1956, people were thinking about this. And in fact, the fundamental papers appeared in 1960. And so the idea is very simple. Astronomers study the universe from the microwave background to the optical, that's the sky you see, not in Madison, but X-rays, gamma rays. So you keep going to smaller and smaller wavelengths, and you discover new things. The things you already know about, you can look at in a totally different way. So this is obviously very successful. The problem is that once you reach wavelengths of about 10 to the minus 15, 10 to the minus 16 centimeter, or energies like 10 TeV. A TeV, a tera electron volt, is the energy of the accelerator at Fermi. So that's my unit in this talk. So once you reach this region, then I'll come back to this later, photons cannot travel through the microwave background. So a photon with this wavelength will meet a microwave photon. There are 410 per cubic centimeter in the whole universe, making it plus or minus pair. And once particles are charged, you cannot do any astronomy anymore. So we haven't seen the universe beyond 10 TeV or so, 100 TeV. So is there anything to be seen there? Well, we know the universe extends because we see cosmic rays. We see cosmic rays all the way to 100 million TeV. So that means that there's about 20% of the universe, at least. Of course, there could be stuff further out, but we are not sure, that we have never seen. You say we've seen cosmic rays, yeah, but they're charged particles, so they're bent in magnetic fields before they reach your detector. And so they don't tell you where they come from. They can be produced there, and they arrive from there. So the sky is scrambled in cosmic rays. So the idea of neutrino astronomy is to see this 20% of the universe that we have never seen. So what is out there? Well, you can speculate. But let me start by saying we have no clue what's out there. We have no idea where cosmic rays come from or how they are accelerated. No clue. There's no evidence. A lot of theoretical ideas that we have repeated so many times, you start to believe it. Like everybody knows that the cosmic rays produced in our galaxy, which are the low energy ones, are produced in supernova remnants. There is zero evidence for this. And but the idea is that when a star collapses to a neutron star, the rest of the star blows out into the interstellar medium. That's what we call a supernova. And like you look at it 1,000 years later, it looks like this. This is in fact a star that exploded 300 years ago. And you see this shock wave. The idea is that you turn a fraction of the gravitational energy from the collapse, you turn it into particle acceleration, 10%, maybe a few percent. And then you can explain the galactic cosmic rays. This doesn't explain the extragalactic cosmic rays that extend all the way to 100 million TeV. But if this object collapses to a black hole, then you can actually get a much more powerful explosion. That's what you saw the movie of here, a simulation. And that's called a gamma ray burst. And so the idea was that these were the sources of the cosmic rays, stellar collapses. There was one other idea, and that is you realize you have to transform gravitational energy into acceleration in some kind of shock wave. And so this can also happen in active galaxies, where there you have these million solar mass black holes, and in the inflow and the outflow of these black holes, you can make shocks. All this is theory, and I'm certainly not going to go into it, although I spend a lot of my life doing this. But this is where neutrinos come in. If one of these objects accelerate cosmic rays, the cosmic ray will say, suppose it's accelerated in a shock along this outflow, this jet. This black hole is surrounded by radiation. So this proton, this cosmic ray, can interact with a gamma ray, P gamma, and make a pion, and the pion decay to a neutrino. So whereas the cosmic ray will be later deflected and forget where it came from, the neutrino will travel straight to IceCube and will know in the sky where this accelerator is. That's the logic. This is very simple physics. So this is what I told you. Black holes, neutron stars are the accelerator. Radiation, dust, molecular clouds, all the junk around these black holes is a target to produce pions. That's how you produce a neutrino beam at Fermilab. You shoot a beam in a target, the pions decay in neutrinos, and out comes a neutrino beam. Same idea. Notice, however, proton and a gamma make a neutron and a pi plus, or a proton and a pi zero. So the pi plus decays to a neutrino, the pi zero to a gamma ray. So for every neutrino you see, you will have to see a gamma ray. We have never seen gamma rays in this energy range. So the conclusion may be you'll never see a neutrino, which most people believe actually. So I'll come back to that later. So this was the slide we would show to sell IceCube to the National Science Foundation. It worked. So what you see here is the sky in neutrinos. This is the neutrino flux, how many neutrinos per unit of energy arrive from the universe. And unfortunately, most of the neutrinos here don't arrive from the universe, they come from the atmosphere. Because these cosmic rays also interact with the atmosphere, make pions that decay to neutrinos. IceCube sees one of these neutrinos every 6 minutes. And in this talk, I wish we did it. But notice, this flux becomes very small. And so at very high energies, there is no background anymore from the atmosphere, and every event is a signal. The predictions, so this tells you how you do neutrino astronomy. It doesn't tell you how big a detector you need. And so here you see what told us how big a detector we needed. Maybe. Notice the flux is multiplied by the energy square. That is because these theoretical predictions, the number of neutrinos falls as 1 over the square of the energy. So 10 times the neutrino, for every neutrino you measure, you have 100 more of 10 times lower energy. That's 1 over E squared. And so in this plot, all the predictions are horizontal. Supernova remnants, gamma ray bursts, and something else I didn't discuss, which was actually the original prediction. And you see you need to build a detector that gets you to this level. And so that means you build a detector that gives you 10 to 100 events per year. And that's a detector, that's 1 kilometer cube neutrino detector. So atmospheric neutrinos will be discussed in a later talk, so I won't discuss this. So here is IceCube, you got the idea. what made IceCube possible is that there was the National Science Foundation had already a research center at the South Pole. And at the South Pole, you stand on 3 kilometers of ice. And so the other side of the runway, you see that's the IceCube project. So to summarize, the project, from the research we did with Amanda, we realized that we go 1.5 kilometers deep, take a kilometer cube of ice and fill it with 5,260 10-inch photomultipliers. That's IceCube. And you have built a Cherenkov. And it's as simple as that. The hardest part is to get the 5,160 into the ice. I won't discuss this either. So the photomultipliers are simple. They're like this. There is a digital optical module out there, which I wish was here, that I could point at it. But so the way it works is, the key is that we mostly detect muons. And so let's stick to a muon 3,000 per second from the atmosphere, and those we definitely wish we didn't detect. And so a muon comes through the detector, it goes at the speed of light. It excites the atoms, which then emit Cherenkov radiation. And that Cherenkov radiation travels through the detector, but it travels at 3/4 of the speed of light. So it leaves the light in a wake behind the muon. And so here is the Disney movie. So you see a muon coming in, it enters the detector. That's the Cherenkov radiation, the shock wave, the bow wave of the boat, if you want. And you see the photomultiplier slide up. The size is how many photons were detected, and the color, which is not very visible here, tells you the direction following the rainbow. So this is the type of muon 3,000 per second, which you have to measure and reject without making mistakes. So in the end, what we detect is about 100 billion muons per year, 100,000 atmospheric neutrinos. This is an order of magnitude more than any other existing experiment, including the supercube. It's a bad detector, but we have many more neutrinos, and you'll see that makes us compete if someone is going to talk about this later. And remember, we are looking for 10 to 100 neutrinos, cosmic neutrinos. So here is how so the detector, the logic was that we would see them at 5 sigma level after 5 years. In fact, we saw them after 2 years, and we saw them in 2 different ways. One way to make sure you have a neutrino is to see it interact inside your detector. Because you see nothing coming in, no light coming in, like in the previous muon event. So it interacts in the detector, and then you see what you get. And you see this Cherenkov pattern, which I explained in a minute. Or you can also make sure it's a neutrino if it comes through the Earth. Nothing but neutrino can come through the Earth. So this neutrino comes from 11 degrees below the horizon. Do it very well. And so this was actually this idea goes back to 1960, Markov. So you look for a neutrino going through the Earth, the neutrino interacts. If it's a muon neutrino, it makes a muon, and you see the muon just like in the movie, except now it comes through the Earth. So obviously it's not a cosmic ray muon, it's a muon made by a neutrino under your detector. And so then you map the shock wave with your photomultiplier. That's actually not what we do, but that was the idea. And so to make a long story short, so here is what you measure in IceCube. So this is now not E squared phi, this is actually the bare number of events. This is how many muons we see come through the Earth. Of course, we measure atmospheric neutrinos at low energy. And then you go to higher energy, you can calculate the atmospheric neutrino flux. It's a well-known flux. So actually, it's a background, but it's also a way to calibrate your detector. We couldn't do this without measuring atmospheric neutrinos over many orders of magnitude. The blue tells you what we should see, and the black is what we see. This is the one event I showed you on the previous slide. And so you see, we see a deviation. We see more neutrinos than cosmic neutrinos, than atmospheric neutrinos. And look, the switchover is at 10 to the 5 GeV, which is 100 TeV, which is exactly at this point. So we see exactly what was predicted. Now, of course, at this point, you assume we are seeing cosmic neutrinos from cosmic accelerators that accelerate high-energy cosmic rays. But we are not sure of that. We should just, the only thing we really know is that we see an excess of neutrinos where you expected to see in a kilometer cube detector. If we hadn't seen it, it meant we had built the detector that was too small. So we were lucky. This is the highest energy event. 1000 TeV is called a PeV. And so no matter what all the manipulations you do with this data, in this event, which is the new one I showed, 2600 TeV of energy is deposited inside the detector. We see it. No speculation about what happened before and after the muon passed through the detector. So here is a movie of this event. You see how it comes in. You see the color, red, green, you follow the rainbow, eventually it becomes blue. This event lasts for 6 nanoseconds or so, so there's no doubt this is a neutrino. In fact, this event by itself is a 4-point-something sigma discovery of cosmic neutrinos, just this one event. More of the same. This is where these neutrinos come from. Doesn't tell us anything right now, although we have ideas. That's a different talk. Is it an e to the -2 spectrum? It's an e to the -2.16 spectrum, close enough with an error bar of 0.11. So typically, high energy sources have spectra between 2 and 2.5. And so this is right in the middle. So that's that. However, this is not how we discovered cosmic neutrinos. The way we really discovered cosmic neutrinos is the way I'm going to tell you next. Remember, you know by now what this is. Now I'll come to that one. That's a cosmic neutrino too. And how did we detect that one? Well, we detected that event just by luck. There was a group in Japan that was looking for something else. Doesn't matter what they were looking for. We do blind analysis, and they looked for what they were looking for, didn't find it, but they found this event. In fact, they found another one like this. And the energy of this event is 1000 TeV, and that's 10 times higher than what you can get from the background, from the atmospheric background. And so this was a 3 sigma evidence, not really discovery, these two events. But the reason this event is a neutrino, of course, is, let me see, I need a slide. Okay, no problem. So the reason it's a neutrino, of course, is because nothing is entering the detector. So you can do an analysis where you require that no light is entering the detector, but that, unlike when a background muon goes through, but the light only starts in the detector. Also, if it comes from in an atmospheric neutrino, it's produced in an air shower, and there are other muons coming along with it. Notice, in this event, there is no muons. There are no muons coming along with it. So the light starts here and then just travels to the neighboring strings. Now you don't see a muon track. It's like someone turns on a light bulb in your detector. So what this is, it's not a muon neutrino, it's an electron neutrino. And so an electron neutrino, what it will do, it will interact. And instead of a muon, it makes an electron. But a muon doesn't have this kilometer range that you saw in the previous picture. A muon will produce an electromagnetic shower, which is about from this wall to that wall. And that shower is like 5 meters long. In a kilometer cube detector, that's a point source. And all these shower particles start to emit Cherenkov radiation by themselves. And so you have this pool of Cherenkov radiation that travels around as if, exactly as if someone turned on a light bulb. So that's a muon track of the same energy. I think you can tell the difference, right? Now this is how big this event is. You know what this is. And so this is the event superimposed on this building. So it has about 100 photons in it. And each of these photons we know to 2 nanoseconds where it is. And it has the size of 5 city blocks. So what it means is that we not only can tell the energy, we can also, from the details, reconstruct the direction. I won't go into this, not very well yet. This was the more than 300 photomultipliers reported. We actually, just last week, discovered an event with more than 400. So this is not a record anymore. So if you measure the energy of these events that are contained in the detector, this is a complicated plot, but the background is really this blue shaded area, and that's the excess. And you see it's well over 5 sigma. I'll come back to that later. So in 2 ways, notice these methods are totally independent and different. There are different energy measurements, different software, they have different techniques, but they give the same answer for the spectrum. So the only other thing you can check at this point, of course this could be anything, but we would like to believe at this point we're seeing cosmic neutrinos from cosmic accelerators like the theorists want us to see. But the only thing, if these neutrinos come indeed from outside the galaxy, I come back to that. One of the surprises, you would think the first thing you would see, like cosmic rays, the majority of it comes from our galaxy. And then there is a small component that comes from outside our galaxy. We actually don't see our galaxy. These neutrinos, as I will show you in a minute, come from everywhere. They are a uniform flux. So if they come from cosmic sources, they are extragalactic. If they come from extragalactic cosmic sources, you can actually reconstruct, they oscillate, but they have equilibrated by the time they arrive at Earth. So you expect equal number of electron, muon, and tau neutrinos, and the data is consistent with that. This is a triangle we always show. This is all electron, all tau, or mu, so we have to find something here, and our data is consistent with that. So, where do they come from? Here is a summary. Let's see, I have 5 minutes. Here is a summary of all the events we have detected that, by the way, we detect in each of these analyses about, in each of them, about 350 neutrinos. Most of these are buried under the atmospheric background. So it's only the tail that sticks out that you can bet your wallet that it's a cosmic neutrino. Wouldn't bet my house. I mean, you have fluctuations, but bet your wallet. So this is where they come from with the angular reconstruction. So you see the muon neutrinos reconstructed to better than 0.5 degrees, and these electron light bulbs reconstructed to some 10 degrees or more. So the action is mostly in the, for astronomy, is in the muon neutrinos, but there will be another talk on this later. Anyway, you notice this says galactic ordinate. So if we saw a galaxy, they will all be here. A galaxy in photons is about 2 degrees wide. So there is no evidence actually, although there are indications that there is some component coming from the galaxy, but none of these evidences have reached 3 sigma. So there's no evidence. There is an analysis which I won't discuss that indicates that fraction that can come from our own galaxy is less than 15%. I think I have no doubt that a fraction does come from our galaxy, but they come from sources in our galaxy that we know and can identify. That's ongoing work. So here are all the surprises. We observe a diffuse flux from extragalactic sources. No evidence for our galaxy at the moment. Remember this slide I showed you that for every neutrino there has to be a PV. You saw two PV, you saw 2 PV neutrino, you saw 8 PV neutrino, 9 PV neutrino. So there has to be a gamma ray that accompanies this neutrino. This has never been seen by an astronomical telescope, right? This was the slide. This is 1950s physics. It's called isospin. Who has ever learned here what isospin is? 1, 2, 3, 4. There's nothing wrong with the rest of you. Just want curious. So, but it is that for every pi, you have to produce pi pluses, pi zeros, and pi minuses in fixed relation. What isospin is. The explanation for this is that a gamma ray coming from this accelerator will make any plus and minus pair. Remember, that's the reason the universe turned opaque. And then this electron, positron, will further radiate. So what it means is you don't see a 10 PeV gamma ray. You see many gamma rays of lower energy. The gamma ray subdivides. Unlike the neutrino, of course, that comes straight to your detector. And you know, only 1 in a million, by the way, don't go straight through. For each event you saw, there are a million we don't see. This is something we have forgotten ourselves. And so what you can do is, this has been done in many complicated ways, but I still remember the first time I saw this at Marcus Alex's desk. What you say, you fit the neutrinos. It's not a fit actually, just drew a line. We said there's an equal number of gamma rays. We dump them in the microwave background, that's electromagnetism. And you see where they come out. They come out at lower energy. And you see they exactly fit this particular description of IceCube. Exactly fits what astronomers see. This is the Fermi satellite, the highest energy measurement of the diffuse flux of the sky. So the surprise is that actually the energy density, you know, you would think neutrinos are something rare. It isn't. There are many neutrinos in the universe at this wavelength as gamma rays. It's just that we see the neutrinos with their original energy, and the astronomers see the gamma rays degraded in energy after they travel from the source to your telescope in a microwave background. So this was quite a surprise. So I have this figure in many other versions, which I won't bother with. So I think this is a good place to stop. So the conclusion here is that this is the conclusion. And so it means we are never going to understand the high energy. You know, there are textbooks on gamma ray astronomy that never mention a pion. I wouldn't read those anymore. So this opens a whole new view, not only a window on the universe, which is the classical thing we say, it opens a whole new view on high energy astrophysics. And so what we have been doing is now doing this analysis in reverse. So now when we see high energy muon that's well reconstructed, within a minute we can alert telescopes where this muon came from, and they can point and see if something is happening there, like a supernova or a gamma ray burst. And the only solid conclusion from this exercise, we only started this less than a year ago, but so this is what's referred to as multi-wavelength astronomy. The only conclusion that shows up to today is this one, that is that the answer is not gamma ray bursts. We have looked at more than 1,000 of them and never seen a neutrino. That's a pretty definite conclusion. So I was going to tell you next about where they come from, but that's a talk that Ali Karandis will give later, next, I guess. Yeah. Okay. Any questions? You must have some questions. Yeah.
So we know that the gamma rays must degrade before they get to the detector. But I imagine they have such high energy that they wouldn't deflect while they're when they annihilate or reproduce gammas. But how much of a deflection would you need in order for them to not be able to resolve it?
Very little. In fact, you can calculate. I mean, it's included when you simulate this, right? I mean, this is physics that's non-negotiable and very well known. And so we know, and the technical name, the transverse momentum that these electrons can pick up and transmit to the gamma rays is on the order of the electron mass. And that's QED. And that's very small. There are theories that speculate that actually the gamma rays don't come from photons, but that they actually come from protons. And then you make an atomic shower that then makes gamma rays. And then, of course, the transverse momentum is of order the pion mass. And then you can begin to search for the width. And people use that to put limits on the magnetic field in the intergalactic space. A less technical question? No? I hope you.
Let's get one over here.
Sorry.
So the PEV energy cascade event you observed, so how did we figure out like is a neutral current or charge current?
We don't know.
Okay.
We don't know. And in fact, I went over the slide very quickly, but the advantage when you look for muons coming under the detector, you only see muons. And you only see charge current interactions of this muon because the muon produces the muon. In the advantage of looking at events starting in the detector is that you see all neutrinos, all flavors, you see neutral current and charge current. In fact, it's a good question because I mentioned this event we just found that there's more than 400 photomultipliers in the signal. We're actually trying to figure out whether the normal electromagnetic model doesn't. In fact, your host is trying to figure out whether this may actually be a neutral current event or a radiation from a muon or maybe a hadronic shower. So this, too won't go into detail, but yeah. So we see, I'm sure we see neutral current effects. questions? Well, I hope you enjoy the week. You know, no matter how frustrating this can get very frustrating, but you should just try to enjoy it. Just, you know, I could never do this because I don't have, you know, you have to be willing to just jump head first into your computer, into the software and into the subject, and try to enjoy it. There's no reason to suffer through this. We let you go at the end of the week. Everybody gets a certificate. So just try to enjoy it, because this is exciting and it's something that's happening right now. You know, as you noticed, to talk to just okay. Good luck.
They should have got the unbelievable the next year physically knows the shift and it's 400 modules, but the effect is outside the effect. So it's half, you see half of it as yeah. It's amazing. It's still a cosmic ray, cosmic new. If this is radiation from a new one, let's say 7, 8 billion, then the new one has to have many times that a typical enclosure step.
Okay.
So this is 7
So,
billion. So you can
our friends entailed that why IceCube exists and what IceCube is actually looking for. And here I'm going to tell you about cosmic neutrinos observed in IceCube and where they possibly could come from, or where to actually look for them. So I'm going to briefly talk about the idea of neutrino astronomy, not from the instrument and how to detect them, but from the fact that how something that we call multi-messenger connected, and how to use various cosmic messengers to look for the source of ultra-high-energy cosmic rays, neutrinos, and what else we can find in the sky. Then we will talk about the neutrino sky and how does the neutrinos cover the whole range of energy in the sky. And then we will talk about high energy from neutrinos observed in IceCube, what are the sources, and what IceCube has told us. So first, let's go through what we actually use here, what are our conventions, and how we talk about and measure stuff. So we're in the particle physics community where the energy is basically in electron volts. The electron volt is the energy of an electron in the potential difference of one volt. So basically, and we use international units where we set the speed of light, the Planck constant, the Boltzmann constant, and in other quantities that you see here to 1. And for some examples, the values that we can get based on the electron volt for these quantities are listed here, and you can convert anything to electron volt using these and considering mass and energy to have the same unit. And these are other quantities that you can refer to as a distance, as the mass, and the other unit that is conventionally used in the astronomy for the energy, which is Earth, which is actually 600 gigaelectron volts. The other thing that is going to be useful to discuss here is the definition of what we use here. So we refer to flux or the spectrum of resources, and the point source flux is the number of events or number of particles per GeV, against per energy, and per centimeter squared, which is the area, and per second, which means it's the rate. And we also talked about the diffuse flux or isotropic flux, which has another component in its denominator, which is the solid angle. So looking at it, so you describe a flux that reaches you from a wide field of view, and you cannot find a point source within it as a diffuse flux, which does not have the same unit as the point source flux. The density of the sources you can find from the diffuse flux by integrating over the energy. So you get the energy part of the flux out of it, and you remain with something that tells you how many sources per centimeter squared per second and per solid angle you have. The energy density could be defined by integrating the isotopic flux multiplied by the energy and integrated over the energy. The luminosity, which is the power for a source, could be defined by multiplying the source by its area. And the mean free path could be defined by the inverse of the density times the cross section, which represents how much is the particle to interact in a target density. So, Francis showed you in the beginning that when you go to the lower wavelengths, which means higher frequency and higher energy, the universe becomes opaque to us unless we use neutrinos. And that basically defines what we call the observable universe. And what does it define the observable universe? And what is actually what's behind it? So, and what we can learn about it. So, this is a cartoon of what the universe may look like. And the modification of the observable universe is basically by the observables that we can have from the universe. And the observables that we can have are the particles that can arrive from the cosmos field, which we call cosmic messengers. And the furthest point that the cosmic messengers can come from tells you where the limit and where the border of your observable universe is. So let's discuss how the cosmic messengers are created, accelerated, and observed at the Earth, and what their limits are. So the cosmic messengers that we have today are gamma rays, neutrinos, and cosmic rays. Cosmic rays are charged particles accelerated at the most energetic objects in the universe, like black holes or in the shocks of a supernova explosion and things like that. The cosmic rays leave the object that has produced them and accelerated them and gave high energies and interact in the cosmic beam gum, where there is enough gas or radiation that the cosmic rays can interact and then produce pions, charged pions and neutral pions. These particles decay into gamma rays and neutrinos, and they all start to travel to the Earth. However, cosmic rays have charge, and the stellar environment and galaxies has magnetic field. So they start to deflect, bend. And when they arrive to the Earth, they do not point back to the sources, their sources. So there is no way to understand where the cosmic rays have come from. Also, if they start to enter to a medium where the density is large, they get absorbed, and we cannot see them anymore. Then we are left with gamma rays. Gamma rays has been used to study the universe for a long time, but the gamma rays interact with the ambient photons and start to create curves which decay the gamma rays, and they also cascade down. So you cannot see the gamma rays after a certain energy that Francis showed in his very first slide. But the only thing that can actually arrive to the Earth is the neutrino. From any object, from any point in the sky. So they can reach us from the furthest points in the universe. They do not interact. That's the nature of neutrinos. They only interact through the big interaction. So they hardly interact. They do not deflect. They don't have any charge. So they are not bent in the magnetic field. And they can point back to their sources. Therefore, they're ideal for the astronomy. And that's why the idea of neutrino astronomy has been disinterested. So, to discuss the source of cosmic neutrinos, we should go back to this picture and see that these particles are produced at the same point. So they can tell us each information around the sources, and they can help us understand the sources of the cosmic rays. So first, let's have a word on the gamma ray sky. So this is the picture from Fermi satellite, which is one of the amazing instruments that has mapped the gamma ray sky. And as you can see, there are a lot of objects in the sky, and the brightest ones are here in the galaxy. If you go to the other observatories, Fermi is a satellite, the ground-based observatories, they reach to the higher energies, but they have less exposure. And what they can show you the highest energy gamma ray sources in the sky. This is a picture from the Hawk Observatory, and you can see this is in the equatorial coordinates, and you can see the galaxy here, and the lasers here, and two other sources in the galaxy, which here you can see the crab, which is the brightest source in gamma ray that has been observed so far. Using the ground-based telescope and their observation, people have created this map, which is referred as the PEV catalog or cascade, which contains the sources of high energy gamma ray that emit neutrinos at TeV energies. And as you can see, a lot of sources have been modified, but no sources has shown to have gamma rays above tens of TeV. So that's the highest point that the gamma rays have reached. And here you can also see something that Francis told you about when you compare Fermi's gamma rays with IceCube neutrinos, which is the extra galactic background light. And as you can see, this drops by 3 orders of magnitude when you reach energies a little above GeV. So the ability of gamma rays to study the very high energy sky is restricted because they are attenuated when they travel through the air. Then there is cosmic rays. Cosmic ray spectrum spans an enormous energy range. And as you can see, it has it features 3 power laws that are separated by what we call the anatomy of the cosmic rays. Basically, this looks like a leg, and here is the knee, and here is the ankle. And the second knee was introduced after this, but the thing is that we know that these cosmic rays have to come from extragalactic sources, because the galactic sources cannot contain. The size is not enough that they contain these cosmic rays with these energies. But we don't know where these cosmic rays are coming from. As I told you, because they bend and they are deflected. But we can study this cosmic ray and see what are the possible sources for these cosmic rays. The first is that there are 2 requirements for a source to be a source of cosmic ray. One is that they have to reach energies that we see in this for different environment. If it's a galactic cosmic ray accelerator, it has to produce cosmic rays up to at least TeV energy. And if it's extragalactic neutrino, cosmic ray accelerator, it has to produce cosmic rays up to at least to these energies, which is about 10 to the 8 TeV in energy. The second thing is that if you consider a source or a source class, like active galactic nuclei or supernova remnant, it has to meet this requirement that if the energetic works, it means that the luminosity that you get from this population of sources, based on how the sources are distributed in the sky and how they are evolved, should integrate into the total luminosity that you can see in this plot. So this is a hint. This is actually tells you what could be the sources and what could not be the sources. Let's go back to the neutrinos. And neutrinos are produced in collision of cosmic rays with the gas or radiation, which means like proton with proton interaction or proton with a photon interaction. And they produce pions, charged and neutral pions, and these charged pions decay to neutrinos. First of all, these neutrinos, if observed, can point you towards the source of cosmic rays. They do not deflect, as we said, they do not absorb, and the other interesting thing about neutrinos is that they oscillate. So if you see a certain type, it oscillates and creates other types of neutrinos. So you could see 3 types of neutrinos in your detector. So, but how does the neutrino sky look like? So this is the neutrino spectrum, or a very wide energy range. And at the lowest energy, you can see that the cosmic neutrino background dominates the sky. This is the neutrinos that are from the early evolution of the universe that has been there from the Big Bang. Then you see the neutrinos that are actually produced in the sun, and then there are neutrinos that has been seen from the supernova that actually happened, that exploded in 1987. And these are the first astronomy that people did with neutrinos. And it had a tremendous effect on what we actually know about how the nuclear physics of the stars work and what actually the properties of neutrinos. Then at a little higher energies, you see that neutrinos from different class of astrophysical objects start to rise. But you see that the atmospheric neutrinos that Ramsey told you is the background for astrophysical neutrino searches is dominating the sky until you reach to the energies of 100 feet. And Francis already told you that above these energies, you can have a clear evidence for cosmic neutrinos. At the highest energy, you have neutrinos that are called DZK neutrinos or cosmogenic neutrinos. And these neutrinos are produced very cosmic rays from the ultra high energy cosmic rays. At the end of the cosmic ray spectrum, interact with the cosmic microwave background, produce a pi plus or pi minus, and that decays into neutrinos. The flux is at the level that you would expect 1 event per cubic kilometer. And that is one of the rationales that IceCube was built for. So what are the possible sources to accelerate particles and produce neutrinos? One of them is active galactic nuclei. Active galactic nuclei is one of the most powerful objects in the universe. That we assume that, or people expect that a black hole is sitting at the core of it, and accretion is going around it, and powerful jets, as you see in this picture, are coming out of the core. One of the other things that is a good candidate for cosmic ray accelerator is supernova. When the diffusive shocks after the explosion would lead to acceleration of particles to very high energies. Gamma ray bursts are also the other option for accelerating particles and producing neutrinos, where the collapse of a star creates a very powerful jet. Gamma ray that we have up to. So let's do a very quick and simple calculation to see how the neutrinos could actually be associated from a cosmic ray spectrum. So assume a generic wind dome where we have a lot of density, and here we only consider the proton-proton interaction. The optical depth of the target that your protons are going to be interacting with it represents how much what the density of your environment is, and is defined by the number density times the length that your particle travels times the cross section. So this tells you what are the properties of your environment. Then, knowing the rate and the spectrum of your cosmic rays, you can use it with along the optical depth to understand how many ions per energy per time you can get out of it an injected proton spectrum. Then you know that for each proton, for each pion, 3 neutrinos and 1 electron are the final particles that are left after the decay. So we know that about 1/4 of the pion's energy goes to each lepton, which is the neutrino. Then we can relate the neutrino rate to the proton rate. And assuming that basically your source, your target is basically proton, meaning that it's at density of the hydrogen, and considering that the current density, which is the density times the length that it travels, and considering the normalization of the spectrum with the cross section, this can tell you what is the neutrino rate at the source. And you can consider the source evolution and population and its distance to relate this to the diffuse neutrino flux that can be observed at the Earth. So the other thing to mention was the cosmogenic neutrinos, the GGK neutrinos, that, as I said, are produced in the interaction of the ultra-high energy cosmic rays with the CMB. Here is the project of what you would expect for muon neutrinos and electron neutrinos from these sources. And the energetics for that is like that. The neutrino from the pion decay carries about 5% of the primary cosmic ray. And there is one neutrino coming out of this process that has about 1,000 of the proton energy. So how are the neutrinos and gamma rays associated with the cosmic rays are related to each other? So we showed you that for any neutrino that is produced in the pionic decay, in a hadronic process, it is inevitable that there should be a gamma ray. That's why Francis brought the question, where is the PV gamma ray associated with the PV event in IceCube? So in a single case, and in counting the number of gamma rays from a source could be related to the number of neutrinos from the source. Here, J represents the flux for one source. And you can see that there is a simple relation, which is modified by the attenuation of gamma rays from the source. As I told you, when gamma rays reach the present energy, they start cascading in the background light, and they don't reach us. So you have to correct for that. And the factor depends on whether or not it was an interaction with the gas or radiation. However, it has to be noted that this relation should be colorimetric. Not all the gamma rays make it to the Earth. Some may be absorbed or cascaded inside the source that we may not have the information from. And they might be also lost when they are traveling through the galaxies. So the discovery of cosmic neutrinos was described by Francis, a clear except at the higher energy. I'm not going to put any time on this. But what are the observables that you have from observation of cosmic neutrinos? What you can learn when you see the cosmic neutrinos? There are 3 different observables, which is one is arrival direction. So you can understand where the neutrino is coming from. This is the map for the 54 events observed in the same channel that the discovery has been made. And you can see that the neutrinos are coming from different points in the sky. Then neutrinos have energy. That energy can tell you what's happening with the flux. And also neutrinos have flavor. And the flavor could be understood based on the topology. So we have a track or we have a cascade inside the detector, and that can tell you something about the flavor. Since the tracks are produced from muons, and cascades or showers are produced from the other particles and muons going through neutral current interactions. So let's look at each of these components. The diffuse cosmic neutrino flux that we observed, we could call it diffuse because we have not seen any anisotropy in it. So it's basically the same through the whole sky. Appears above the atmospheric background that we have. And here you can see in green the high energy starting event analysis results that showed us there is a cosmic neutrino excess. And then you can see another channel for IceCube to observe cosmic neutrinos, which is the through-going muons, which showed us the highest energy neutrino that you have, that Francis showed you also. So you see that they do not cover the same range of energy. And you see that this flux is a little steeper than the one here. And that tells you that there might be some hint of features in the spectrum. It means that the flux may not be a simple power law. It cannot be described by a single equation. And that tells you that there might be different sources and population of sources that are contributing to this flux. So this is what we know so far about the flux of cosmic neutrinos. Then it's the arrival direction. You see this plot in Francis's plot. So it shows you the events in 4 years of high energy starting events in green, and the muons that are seen in the through-going sample. The through-going sample is restricted to the northern sky, basically. So this is the horizon, this is the galactic coordinates, this is the galactic plane, and you see that the red circles are all above the horizon. And that's where IceCube is most sensitive, because the atmospherics are suppressed by the air. But it came to the price that the absorption of the neutrinos in the core of the Earth also grows when we go to the higher accumulations. And that's why you see that the most of the events are kind of populated to the horizon. And that's actually the most sensitive point for IceCube to look for the sources. So the arrival direction has been studied for all these samples, and no indication of anisotropy has been found. So there is no correlation with any class of sources, or there is no autocorrelation, means no clustering of the events so far. And for the Hesse sample, people have studied the association with the galaxy, which we know cosmic rays are associated to. But so far, no association in neutrinos with the galaxy has been confirmed. But we cannot exclude that possibility. This is the dedicated point source study in IceCube. And this is what you see here is basically the statistics. It tells you how, if you have any clusterings of the events at each point of the sky. The hottest spot in the northern sky is defined to be here, and the southern sky is defined to be here. However, none of these hot spots have enough statistical power or significance to be confirmed as a point source of neutrinos. So the last observable from the observation of cosmic neutrinos was the flavor. And what actually flavor can tell you is that what scenario in which neutrinos may have been produced. So focusing on this plot, if the pionic decays were responsible for the production of cosmic neutrinos, you would start with this fraction of muon neutrinos and electron neutrinos. So this triangle basically tells you how much of fraction of each flavor type you may have. And then traveling through the Earth, they oscillate and reach to this point in this problem. The other case that could happen is that the cosmic rays interact with the matter or gas in a very magnetized environment. So the muons get trapped and they cannot decay. So the muons are suppressed. And the only component that we get is at the beginning is a muon neutrino. So the muon does not decay to produce another muon and electron neutrino for you. After oscillation, you reach to this point in here. And if your sources are producing neutrons, not pions, so the cosmic rays, cosmic neutrinos are as a result of neutron decays, which produces electron neutrino, then you would start from this point in triangle and would reach to this point. So basically, whatever scenario you start with, is you would land on this line here. So this is the prediction. If you go to what we have observed, this is the best fit point, and this is the contour that define how likely for these events to be found in this area. So this is basically what we have seen, and this is the and it shows you that this point, which was the neutron decay, is not supporting the data. So the most likely scenario for us would be the pionic decays. So what we know about the cosmic neutrinos so far? So IceCube, first of all, has observed neutrinos in different channels. So it has confirmed in two different analysis that the excess of cosmic neutrino flux exists. The highest energy neutrino that we have observed had deposited about 2.6 PeV energy, and that is the deposit energy from the muon that passed through the data. The most probable energy of that neutrino, the neutrino that produced that muon, is about 10 PeV. So this is the highest energy neutrino that is observed. The other thing that we understood from the observed neutrino is that the arrival direction of neutrinos is compatible with the isotopic background. So far, IceCube has not been able to pinpoint a point source in the sky. So we don't have any clue what these neutrinos are coming from. The galaxy is one of the important places to look at. We know that the galaxy is producing cosmic rays up to the mean in the spectrum, but it is not contributing more than 15% to the observed flux. You can see that from the arrival direction. And where is the PeV gamma ray that we would expect? So we have looked into a variety of gamma ray sources and catalogs to see whether or not there is any correlation with any sources there. And we haven't found anything yet. So the other interesting things that we have learned from the cosmic neutrinos is that hadronic accelerators are not a small fraction of the high energy sky. The non-thermal universe has a large fraction of its energy from hadronic interactions, which is basically manifested in neutrino observation. The interesting thing is that if you look at the ultra high energy cosmic rays observed by Usher, and the neutrinos which you see nicely, and the gamma rays inferred from the background light, you can see that the same amount of energetics are in the tree, and that basically shows you a unified picture of all the high energy cosmic rays, gamma rays, and neutrinos. Do we know why that happened? No, it can be accidental, but it can tell you that these may come from the same place. These may have the same origin. The other thing that Francis briefly talked about, and I'm not going to spend any time more on it, is that you can find the isotopic gamma ray background that Fermi sees by starting from neutrinos in the IceCube. So, and there are a variety of sources in the sky. The most important ones are active galactic nuclei that can be seen in blazars, radio galaxies, and then there are starbursts that are calorific, and they are enormous amount of them in the sky, and they're far, and we cannot resolve. And what we have seen so far in IceCube, and the limit on the point source and our sensitivity, tells you that these sources, which have a lower density in the universe, but are bright, are less likely to be the source of IceCube neutrinos. And these sources have a higher chance to be the source of cosmic neutrinos. So, in summary, high energy neutrinos can tell us where the cosmic rays and ultra energy particles are produced and coming from. They are not deflected and they are not absorbed, so they can point toward the edge of the universe for us. The discovery of IceCube opened the new era of neutrino astronomy and has been with a lot of surprises. It's going to be amazing. What are the sources? What can they tell us about the source of cosmic rays? And where is the PV gamma associated with the PV neutrinos? These are all the open questions, and these are what IceCube is going to look for in the next year. Francis told you about the multivariate astronomy and how we have seen the sky within different energy ranges and wavelengths. So this is the picture of the galaxy, looking in the hydrogen, the radial of X-ray. And the neutrino picture of the galaxy is missing. So let's see.